Hi guys, in this video we're going to start the probability slides, start with the basic concepts and work on up to independence and conditional probability in subsequent parts. So probability starts with this basic concept of a chance experiment. This is any situation where there's uncertainty about which of two or more possible outcomes will result. We have this concept of a sample space, which we use the capital letter S usually to define or to name. What it is a collection of all possible outcomes of a chance experiment. So for example, if you're flipping a coin one time, the sample space is indicated like this. Okay, using set notation here. And if you're flipping a dime and a nickel, or two coins in other words, the sample space is represented like this. If you're rolling a six-sided die, there's 6 possibilities and they're labeled 1 to 6, and we can indicate the sample space like this, okay? So an event now is a very important concept. This is any subset of the sample space, and technically speaking, the sample space itself is a subset of itself, so therefore it can also be thought of as an event. Okay, another often overlooked event is the empty set. Okay, that's a set that contains nothing, or a null set. Okay, so but putting that aside for the moment, coming back to that later, if the outcome of the experiment, this chance experiment that we're talking about, is contained in the event, then we say that that event has occurred. We usually use capital letters from the beginning of the alphabet to denote events, because we want to stay away from X, Y, and Z, and T even, and U and V, because those usually we reserve for variables. So A, B, C, D, E, F, G is very common. If you need a lot more than that, you can start using some subscripting. So for example, if I arbitrarily define rolling an even number on a 6-sided die, so back to this chance experiment where this is the sample space, and I define an event arbitrarily as rolling an even number, then I can call that event E, or whatever I like, A, B, whatever. And here are the outcomes that satisfy my definition of E, or the event E. If now I go ahead and I roll the die, and one of these outcomes appears or occurs, then we say that E has occurred. That's what we're saying here. Okay? So if I roll a 2, then E occurred. If I roll a 4, then E occurred. If I roll a 6, then E occurred. Obviously, I can't roll both or all 3 of those, rather, because I'm rolling a 6-sided die one time. Okay, so that's an event, very important concept. Now let's do something a little bit more interesting. Let's just start with this kind of very abstract scenario where we're going to let A and B denote 2 events. Okay, so just any 2 events, and keep it abstract. There is an important event called the complement of A. So the event not A consists of all outcomes that are not in the event A. Okay? The different notations that you'll see across textbooks are listed here. I'm going to use these Venn diagrams in the subsequent slides, so let's just describe them a little bit. This box right here represents the entire sample space. So all the possible outcomes that can occur in any chance experiment are within that box and nothing else. Okay? Now, within the box we can play around. So how we're going to play around is drawing little circles here and there, little shapes. What this represents is outcomes that satisfy the event A. Okay? And anything outside of this are outcomes obviously that don't satisfy A, or that are not in A, and we call that the complement. So in this particular case, everything outside of that circle is the complement of A, and I've noted that here. Okay, so this makes it visual. Here I've shaded it in blue, the complement of A. Next, let's look at the union of two events. So if I let A and B denote two events again, A or B, or A union B, are all outcomes that are either in A or B. So it's very inclusive, okay? This is called the union, and this is how it's notated, okay? So here's two scenarios. So call this scenario 1, scenario 2. Let's take them in turn. First off, in scenario 1, we see that there's no, what I'm going to call right now, overlap between the two events. Notice they don't overlap each other. Okay, we're going to have a more technical word for that in a moment, but for now, just visually, there's no overlap. Okay, so here are all the outcomes that are in A, and here are all the outcomes that are in B. We should fully shade these. Okay, now where is A union B? Well, let's read the definition again. All outcomes that are either in A or B. So that would be everything in A and everything in B. That would satisfy the union. Okay, so where I've shaded is where A union B would be. How about in scenario 2? So this is another fundamental possibility that can occur, another scenario. All other scenarios are going to be complications off of these two very simple possibilities. Okay, now scenario 2, clearly you see there's an overlap between the two. This overlap here, we're going to have a name for in a moment, but for now, let me just call it what it looks like, an overlap. But more importantly, back to our question for this slide is, where is the union? I want to shade the union. Again, all outcomes in either. So that means all of them in A and all of them in B. And why not the overlap as well? Aren't those either in A or B? They're in both, so perfect. Okay, so the union would be all of this shaded. Okay, and then the next slide, I'm going to do that more cleanly in blue. You can see where the unions would be in the two scenarios. Okay, we're going to revisit these scenarios again now in the next concept called the intersection. So in the intersection, these are all outcomes that are in both. Notice not the word either, but must be in both A and B. This is called the intersection, and it's denoted with this upside down looking U. Okay, so that's the notation. That's read A intersect B. Okay, now in scenario 1, there's no overlap. Let's think about where I want to shade where the intersection is. Well, which outcomes are in both of them? They don't share any outcomes because there's no overlap. There's no intersection, more technically correct term. Okay, so I have nothing to shade here. In fact, you can say that the intersection here is null, and we use this notation sometimes to indicate that. Okay, let me attempt that again. There. Okay, the intersection here is null. The intersection here, remember, this is where there is overlap between the two events. The intersection is where the overlap is. This area that I'm shading right now are outcomes that are in both A and in B, so they satisfy the intersection. Okay, again in the next slide I'm going to shade this more cleanly. As you can see, there's nothing to shade on the first scenario. It's an empty set. On the second scenario, the overlap. Okay, the intersection. Great. Now moving along, we have this idea of disjoint or mutually exclusive events. We've already been talking about them, but now we have a more technically correct term for them. These are two events, and we're keeping all this to two events for now, but this can easily be generalized to 3 or more events as well. Two events that have no common outcomes. So in this case on the left, scenario 1, these two events don't share any outcomes. Their intersection is null or empty. Okay? How about in scenario 2? This is different than the scenario 2s from the previous few slides. This is just an event and its complement. Think about that for a second. An event and its complement are by definition disjoint or mutually exclusive. they don't share any outcomes. Why? Because the complement of an event, B complement, contains all outcomes of B that are not in B rather. Okay, so these two are also complementary, as well as this possible scenario here. Okay, all right, so that's an important concept, disjoint mutually exclusive events. All right, so here's a little example we can work on. So we have we have to select 2 students randomly to get an award from a group of 5 students. They're equal awards. It's not a first place and a second place. Of the 5 students, 2 of them are female and 3 of them are male. Okay? So first thing I want you to do is to list out the sample space. List out all the possible outcomes that can occur. Okay? So if you do that, you're going to end up with, and we should use this notation, you're going to have to come up with some kind of naming convention. So what I'm going to do is say female 1, female 2, male 1, male 2, and male 3. Okay? So first possibility, in no special order, could be female 1 and female 2 get the award. Okay? Second possibility, female 1 and male 1 get the award. Female 1, male 2. Female 1, male 3. Female 2, male 1. Female 2, male 2. Female 2, male 3. Female. We're done with the females, so strike that. Male 1, male 2. Male 1, male 3. And male 1, 2, male 3. Just make sure you don't miss any. The order that you do it does not matter at all. Let's count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does the order I write these matter? No. For example, what I mean by that is female 1, female 2 the same as female 2, female 1. Yes. Why? Because there's no first place and second place. The order doesn't matter here. This is important for you to recognize. There's nothing in the wording of the problem that indicates to you that the order matters. If the order mattered, for example, they said, we need to pick 2 students out of 5, and there's going to be a first place and a second place. Well, now all of a sudden, F1, F2, for example, is one possibility, and F2, F1 is another possibility. Do you see that? Okay? And that would just double things, by the way, if that was the case. But in this case, there are 10 possibilities. Okay, so let's answer that question. That's an important number to know as we go forward. Define event C as selecting at least 1 female. So here we go. We're told to define an event, call it C. Okay, and this is at least 1 female. So that would mean this guy, female 1. Well, instead of writing them, let me underline them here. This guy, this, and not these 3. So these 7, there's 7 of them, would satisfy my event C, at least 1 female. Do you see that? That these last 3 in my list at least are not at least 1 female, and that these are. Okay? Good. In words, so if you could go ahead and list those out. I just underlined them. Okay? 4. In words, what is the complement of C? So what is C complement? Well, in words, let's just think about it. We could list it out. It's going to be these guys over here, right? In words, you can put that, because I'm asking you for words, getting 2 males, or both the males, or not there because there's 3 males. Only males getting an award, or no females getting an award, or exactly 2 males getting an award. However you phrase it, what you're indicating here with C complement are these 3 outcomes, okay? Which you can also list out explicitly. Okay, so take a little snapshot of this because we're going to probably come back to this question when we build up a little bit more and answer some other problems. So this sample space is going to help us a lot. By the way, if you have questions on how you can arrive to this number, how many possibilities without having to list this out, be sure to watch the tutorial video on the binomial distribution where I show you the binomial coefficient, which actually in the process of learning other things, you're going to learn how to calculate how to get this number without having to list question 1 out, the sample space out, especially useful if your experiment is much bigger in number than what we have here. Okay, so watch that video on binomial experiment, binomial coefficient. All right, moving along. Now, finally, a definition for probability, and in a classical sense first. Classical probability can be applied when the outcomes of the sample space are equally likely. So if it makes sense and it's reasonable that every outcome is equally likely, when you flip a coin, 2 sides are equally likely. When you roll a die, the 6 sides are equally likely. Okay? Then you can apply this, then you can compute probability, arrive at probability rather, with this very simple ratio. So first off, some notation. So we use capital P, and in parentheses, we put the event that we're interested in. Okay? So this is read, the probability of the event E equals, okay? And this is just a counting function, so cardinality of a set, so you don't need to read too much into that. You can see what it means here. Basically, all you need to do is to get the fraction of the number of outcomes that are favorable to the event E over the total number of outcomes in the sample space. Okay? So now going back to our previous problem, continuing, what is the probability of C? Do you remember that there was 7 outcomes that were favorable to C on the previous question that we did? So that would be in the numerator over the total number of outcomes in the sample space, 10. That would be the probability of C. So counting is the hardest part oftentimes of probability. Okay? Because once you know the counts, then you can easily get the probabilities with this simple ratio. Okay, what's the probability of the complement of C? Well, again, there were 3, if you remember, outcomes that did not satisfy C. So that will be 3 over 10 over the total number of outcomes possible in the experiment. Another way to arrive at this is because of the nature between an event and its complement. Because together they fill up the entire sample space. In other words, an event and its complement leave no outcome untouched. Therefore, you can take the probability of an event away from 1 and arrive at its complement. Okay, this is something we may check in the next slide, but you could go ahead and check that 1 minus 7 over 10 equals 3 over 10. So that could save you a lot of time in some cases. Okay. Okay, moving along. Some fundamental properties of probability. First off, some obvious ones, but worth mentioning. For any event E, the probability must be between 0 and 1 inclusive. So if you get probabilities that are negative or probabilities that are greater than 1, you've done something wrong. If the probability of an event is 0, that means it will never occur. If the probability is equal to 1, that means it will certainly occur. Okay? The probability of the sample space, that special event, if you like to think of it as that, is 1, because it's going to be the total number of outcomes in the sample space over the total number of outcomes in the sample space. So in our case, it would have been 10 over 10, 1. So that will always be 1. Another way to think of this is saying, what's the probability that something's going to happen? Well, 1, right? Not so interesting, but good to note. Okay? Next, 3. The probability of a union of 2 events. Okay, we talked about what unions were, right? Is the probability of the marginals, we call these, the individual events, added together minus, this is very important, the intersection. That was the outcomes they had in common. Now, why do you think you need to do that? Well, let me just flip back to one of these slides here. So if I want the probability of the union here, that means all this, right? Watch as I shade, okay? I'm going to add this guy to this guy. Notice when I add this guy to this guy, I counted the center twice, the intersection twice. Therefore, I subtract one of those intersections and I'm left with just the one, okay? Listen to that again if that was too fast. Rewind. That's why we subtract one of the intersections when we want the union. Now, if the events, E and F, A and B, whatever the two events are known to be disjoint, in other words, it looks like the scenario here on the left. Okay? Here, let me go to this one. On the left. Then you simply sum the two marginal probabilities. It's as simple as that because there's no intersection here like there is here to have to worry about. Okay? And in fact, if you want to think of it a little bit deeper, the intersection here is an empty set, the null set. The probability of an empty set is 0 over whatever, so it's going to be 0. So it's like you're subtracting 0, so it works out nicely. Okay? So coming back to this, if the two events are disjoint, then the probability of the union is simply the sum of the two probabilities because the intersection is equal to 0. And then the fourth and final fundamental property of probability that I want to talk about is that for any event, E, A, B, C, whatever, the probability of E plus the probability of the complement of E is always going to be equal to 1 because they fill up the sample space. Together, they contain all the outcomes that are possible without any overlap with each other. Therefore, something we saw before, the probability of a complement is equal to 1 minus the probability of the event. Or you can flip that depending on which way you want to go. That could save you a lot of time, and we already saw that in the previous question on the previous slide, question 6, where we got the probability of complement of C by doing 1 minus the probability of C that we did earlier. Okay, moving along. So let's check property 4 for the problem. This is a continuation. Property 4 worked out, right? We did that already. That's what I just talked about. Now let's define another event, D. So event D is awarding only one male. So only one male. Let's just, instead of listing this out, go ahead and list it out. Actually, you could pause. I want to know how many outcomes satisfied that. So only one male. If you remember the sample space, go back in the video. I can't go back in the video at this moment, but go back and count. If you're counting correctly, you should arrive at 6, I believe, because you're not going to include the ones where both males get it. There were 3 of those. And you're not going to count the one where both the females get it, because no male would get it there. So there's 6 left. So there's 6 possibilities. You should list them out, okay? Now we move along. Now we have 2 events. C, which was at least one female. D, which was one male exactly. And now we want the union. Is there an overlap? Which I'm jumping ahead a little bit, but this will be useful information. Of course there is an overlap. Of course these 2 events are not disjoint. Just think about all the outcomes that they share. For example, male 1, female 1. That satisfies D and it satisfies C. It was in both of those. Right off the bat, you know that these 2 are not disjoint. They're not mutually exclusive. Now the question becomes what the probability of this is. So we sum up the 2 probabilities, probability of C plus the probability of D minus the intersection of the 2, which we now have thought through and we know there is an intersection. So we have this from the previous slide, 7 over 10, and we know from question 8 that there's 6 outcomes that satisfy D over 10 total possible outcomes in the experiment. And then now what is that intersection? Now go through and count how many of those outcomes are shared between C and D. That's the intersection. It turns out that exactly 6 of those outcomes are at least one female and exactly one male. There's a big overlap. In fact, if you draw this at the Venn diagram, you would see that D is a proper subset of C. It happens to be that case. There is a huge overlap between the two. D is inside of C. It's to that point. Okay? And so the answer here would be 7/10. And what about the intersection? Well, we answered the intersection. So question 10 was answered in the process of answering question 9. And question 11 was answered in the process of answering question 9 as well, because we saw that the intersection was not equal to 0. If the intersection, the probability of the intersection is not equal to 0, then it is not disjoint. If it was equal to 0, then you say that C and D are disjoint. So the answer here is no. All right, let's see. Oh, so maybe one last slide with some useful properties for probability that you might want to look at. Let me just point them out. The cumulative, the associative, and the distributive. Similar to your algebraic and arithmetic properties. So cumulative says A union B equals B union A intersect B equals B intersect A, so the order you write those doesn't matter. And just take a look at some of these other ones. It's don't need me to talk through them, but that's essentially this is a good reference slide in a case where you need to do some kind of probabilities with more than 2 events, and there's parentheses, etc. involved. All right, so I'm going to pause this one here and then come back with a part 2, 3. I don't know how long it'll go, but we still have some more topics to go through in probability. So till next time, have a great day. Make sure to subscribe, like, and share these videos as well. Have a great day. Bye.